want to use, what type of devices you're measuring, any applications that you're looking for specifically that you want to get a deeper understanding of. Everybody here understands S parameters, right? Is that fair to say, or does somebody need a refresher? Okay.
Yeah.
Okay, sure. So we're talking about two-port networks, right? So filters, amplifiers, most devices, unless you're talking about circulators or switches or muxes, you're going to have a number of different standard parameters that you think about when you're doing measurements, right? The first is, if you're an RF designer, the first thing that you want to think about is power transfer, right? So what you need to do there is to have a good impedance match between your building blocks, right? So if you're building a transmitter chain or a receiver chain, you want to make sure that both, for example, if you're saying maybe a down converter followed by an amplifier on a receiver, you want to make sure that the input match between your converter and your receiver are matched, right? So that you can actually get really good measurements. So I'm going to say that you guys agree to use Windows and all that stuff.
It uses Windows 10?
It's Windows 7.
Windows 7.
It's Windows 7 based. Based on two ports, we have a number of ports squared in terms of the S parameters, which stands for scattering parameters, not scalar. So these have magnitude and phase. They break out into reflection and transmission parameters, right? So the ones in terms of that have the same number in the subscript, so S11, S22, are reflection. Yeah. So the sometimes called return loss, right? And so we have our port 1, port 2 return loss, so that's our input-output match. And we also have our either forward loss, forward gain, depending if it's a passive or active device. And then we also have our reverse
transfer.
Yeah.
S1, 2,
S1, 2, and S2, 1. So what you guys have is our PNA-X, and this is our highest end network analyzer. But this is, in addition to just being a standard network analyzer, you can think about it as a software-defined instrument. So when you take a look at this, right, if you go to just the measurements that are available here under measurement class, you guys have a number of different sort of measurements. So you have the ability to do standard measurements, and you also have the ability to do noise figure. But if you were to look at sort of the available options on this particular unit, you could do things like gain compression. If you had a second source, you could do things like intermodulation distortion measurements for an amplifier. And obviously you can do all the standard S parameter measurements. So if you're measuring just a standard filter or amplifier, and all you need to do is just gain over frequency or gain over power, you can do that as well. Now you have two ports, so that means that you can measure a two-port device. If you're looking at, do you guys never need to do frequency converted measurements? Like a mixer, is that something that you guys would typically measure, or sometimes maybe?
What your professor was mentioning that all types of antenna characterizations they will be working on, like S parameters, X parameters, noise figure analyzers.
Okay.
So yeah.
So if you're looking at antennas, right? So it's kind of a little bit. Sorry, you had a question, or?
Just say it's one port.
Yeah. So So antennas are typically one port unless they're differential, in which case two port. And you can do a differential return loss measurement with a two port, right? Because now you have your positive and negative on your differential, and you can just still do your two port balanced topology. Now, do you guys ever build differential antennas, or is it mostly single-ended antennas?
Just single.
Single-ended? Okay. I'll show you guys how to do. We'll do both, right? So this gives you access to all the different features, and you guys also have a number of different calibration kits available. And I'll talk a little bit about sort of the different things that you can do with your different calibration kits, and what the difference between them is. Okay. So, who's done a network analyzer calibration before? A couple people? Okay. So, because we're actually measuring vector parameters we can apply something called vector error correction. So typically one of the things that you want to do is you want to know what the gain of your device is, not the gain of the device plus the cables and the measurement system and everything around that, right? So if I just want to get a rough idea of what the device performance is, I can just hook up my cables and do a measurement, but that's not an accurate measurement of the device's performance. So in order to do that, I have access to this, which is an electronic calibration module. And you have two, and I'll kind of explain the difference between these two and why you need to have two. So the first one, which is this one here, is the one I would recommend for most of your measurements, especially if you're doing antennas. And the reason for this is this one is metrology grade, so it's actually controlled with an oven, and will actually bring the electronic standards up to a certain temperature before you can do the calibration. So you'll see there's a wait and ready light on here. And so what it does is it has a number of electronically tunable loads that are available inside the network analyzer. And these, inside the calibration module. And these need to come up to a certain temperature so that when we've characterized the response of these loads, we want to make sure that when we're doing the calibration, the temperature within the standard is the same as when it was initially characterized in our calibration facilities.
So I mean, it has built-in circuits inside so that we can test with this module?
Correct. So it transfers over USB, and if you say to the network analyzer, calibrate, and I'm going to do just a smart calibration, and I'll go through some of this here. But as soon as you say this, it actually knows that it has, this N4691. It knows that it has, assuming you're using a 3.5 male device, right, or a 3.5 female device, because that's the kind of standards that you have on this unit. So it assumes a type of connector. So most of the time, I'm guessing you guys are going to be working with SMA, maybe occasionally type N. So mostly SMA. Is that fair to say? Yes. So 3.5 and SMA are mechanically compatible. There's a little bit of a difference. Do you guys know what that is between SMA and 3.5? So it's the dielectric, right? So if you take a look at an SMA cable, it has a Teflon dielectric, and what happens is that the cable starts to mode. So it starts having more than the standard modes of propagation that you want, more than one, at around 20 gigahertz. And so that's why typically SMA cables are rated to just 20 gigs and you can't use them beyond that. But 3.5 millimeter uses an air dielectric. It also has tighter specifications for the quality of the distance between the two inner and outer conductors. And so it means that it's going to be a more precise type of connector. And that one is actually rated to typically 26.5, but sometimes you can get to about 30 gigahertz with a 3.5 millimeter connector. So I'm assuming you guys have some test cables that also came with this somewhere?
Test cables? I don't.
You don't have test cables?
So what types of cables you're looking for, like DNC?
Coaxial or
Yeah, coaxial cables.
any
We have
SMA, yeah, you got some or no? You guys didn't get any as part of your kit?
some BN.
BNC is okay, right? Or conveyors okay?
No. Okay.
SMA.
We have some BNC. I'll bring the BNC.
Okay, so I think that's something we'll have to talk about as well, because I left mine back in my car, so that it's a bit of a walk to get back there, but we can if we have to, I can go and get some actual test cables. Do you guys have a device, like a filter or something you want to measure today, or no? If not, again, that's totally okay. We can go through that at a later point, but I just wanted to see if you guys had something that you wanted to measure. So what frequencies are you guys typically work at? What kind of, is it mostly cellular band, like sub 6 gigahertz stuff, or do you guys go up to some X band for radar? A bit of both, or? Sorry? Sub 6?
Like typically below 10 gig.
Oh, below 10 gig? Okay.
But most of the research is like low frequencies.
Okay. So what would you define as low frequency? Like hundreds of megahertz? Hundreds of megahertz? Okay. So the reason that you guys may be more used to using BNC is that because obviously BNC works till about 1 gigahertz, right? The connector is rated to about there. The issue with using BNC to do really good measurements, and maybe this is what you guys have here.
This is some of the courses you purchased. So you have BNC to navigable, BNC,
Okay, so you have
some
some
SMA as well.
Okay, so you have some SMA, and it looks like you have
Some connectors, adapters.
okay, adapters. Okay, perfect. So these are. So this is the SMA. So you guys, can I'm going to take 2 barrels from here. I'll talk a little bit about, and you can pass this around if people want to take a look at it. So the main thing that you want to do when you're doing your measurements is to think about sort of what you're going to connect to. So you may end up connecting to BNC, but the first thing that you do before you even connect it to the network analyzer is visually inspect your connectors, right? So a lot of the times I go into some labs, especially undergrad labs, connectors will be lying on the ground, sometimes they fall, you might get damaged, right? The worst thing that you want to do is not check your connectors and then connect them to your network analyzer. And what will happen is that you will then damage the ports on the network analyzer, right? This is the really expensive instrument. Repairs are pretty expensive. So what I typically say to most of my customers is to just keep a set of bullets on the network analyzer. That way, if somebody's not careful, they connect a bad cable, they're going to damage the bullet. They're not going to damage the network analyzer. The bullets are probably $50 on DigiKey. Network analyzer repair for the front end is like $18,000 or something crazy like that. So, that's the main kind of takeaway from this. The other thing that you want to do, right, is you'll see there's a male and female part of the connection. You always turn the male outer nut, right? So, if you think about that, why am I not turning the female part of the connection? So, if you take a look at the bullet, right, or if you take a look at the cabling, you have an inner conductor, right, and then you have an outer mechanical jacket. So this is part of the shielding. It's meant to take mechanical stress. That's why the thread is here. If I rotate the whole cable or the female adapter as a whole, I'm putting mechanical stress on the inner conductor. That's where the RF signal goes. That's no good, right? So what I want to do is I always want to rotate the female part. You probably don't have to deal with this when you're using BNC, but we'll talk a little bit about why it's important for this. So what I'm going to do is I'm going to do a very basic calibration, right? So maybe you want to do just a very basic one-port antenna measurement, right? And you'll see that you get some kind of ringing at the end. And so you might say, okay, well, why is that? what's going on there. And part of that is just simply because of the outer jacket. If I rotate this outer jacket, I'm changing the fringe capacitance at the end because I have the pin sticking out from the male connector. So one of the ways that I can see kind of how good everything is just to say, okay, well, what happens if I just use a female adapter in here? Because this is not really an open, right? It's an open plus some fringing capacitance that is variable. But if I use a bullet, I can take a look at a little bit more interesting things. And what this might tell me is actually this response is coming from the cable jacket itself. So this kind of tells you the quality of the cable that you're using. When you're using a vector network analyzer, what I really recommend is that you think about the quality of the cables that you're using, because I'll kind of show you guys some ideas of this. Because you're applying error correction that's not just a magnitude offset, you're applying corrections to all the error terms, so the reflectivity, directivity, phase tracking. If your phase of your cables and your whole measurement system is changing as you're doing your measurement, then the error terms that you initially measured when you did the correction are no longer valid as your system response is changing, right? So that's why you have to use really, really good cables attached to the network analyzer. And then beyond that, that means that the system response is going to be very well characterized, and all you're measuring really is your device. So let's take a quick look at doing this calibration and kind of getting a feel for it. One other piece of advice I give you is just to cover up your connectors. If you have the SMA bullets, it's not as critical, but I'd still recommend it. The reason for that is, especially with these high-end connectors, because the dielectric is air, if you leave it open, then dust gets in, and the dielectric is no longer air, it's air plus whatever dust gets in there. So that's something just to think about. In terms of the measurement, what you really want to think about are sort of, I guess, three things. First of all, what's the frequency range that you're going to measure? And this is probably going to be the most critical thing for you guys. So, you just hit frequency here. There's a start-stop. There's a center span. Whatever method you guys prefer to specify. There's also for the sweep, you can also set the number of points. Again, depending on what you're going to do with this data, if all you're going to do is just plot the graph, then 201 points is typically fine. It's not really a big concern. Are you guys going to be taking this and then using this in a simulation model or something like that? Like maybe HFSS or ADS or Sonnet? What do you guys use for your antenna design?
ADS.
ADS? Okay, that's good. It's a Keysight tool, so I'm happy about that.
Yeah.
So if you're using ADS and momentum, which is the EM part of it, then what you're going to probably be doing is maybe taking an S parameter file, right? And so depending on the frequency resolution, you may want to increase this. So there's your frequency, your number of points, right? For passive devices, this other setting is not going to matter, and that's the power, right? Let me amend that. It's not going to matter too much, right? So there is a certain point after which, if I lower the power that I use for the measurement, I'm getting closer and closer to the noise floor of the instrument, which means it's no good. And there's also a consideration where I may, if I have a very sensitive device, like maybe a sensor receiver, which is something I think that you guys do quite a bit, then I don't necessarily want to put in too high of a power into that sensor, right? So I may need to think about, okay, what is this sensor typically getting? And if I take a look at sort of, again, one of the things that we can do really quickly is just take a look at just about the network analyzer that you guys have. And so you have the noise figure option and the internal noise receiver. Sorry. And and so that's all the options for noise. But what you can do is there's an option to add like a lot of attenuation inside. So I was just at a customer this morning who measures beacon receivers for satellite, right? So these are extremely sensitive devices. You have to get a signal from space, so they cannot stimulate their device with more than minus 60 dBm of input power. So they either have to use external attenuators, or the network analyzer has an option to build in attenuation to allow you to go down to as low as minus 90 dBm of input power. So that gives you a lot of flexibility in what you're doing. So for you guys, I think since you're doing
the maximum?
What's the maximum power? Depends on frequency, right? So you can easily get, I'd say, probably around plus 13 for the full range. So if you go and depends on sort of I think at the low end you might be a little bit more limited. So if you're going below 100 megahertz, that's where you might start running into issues. But you could easily get 10, and there's no issues. You might even be able to get, like I said, about 13. So that's fine. Probably anything above 13 dBm, I might see a warning come up saying source is unleveled, and that's where I would have some issues. But we can go, say, what I typically recommend is that you probably use for passive devices about -5. The reason for that is it kind of helps you, -5 to -10 is good. The reason for that is that the eCal typically compresses around -5. So you'll see if you look at this, it says, sort of maximum power is plus 10 dBm. That's the damage level. So don't ever put plus 10 dBm or more into the electronic calibration module. You'll damage it. But you can go, -5 is sort of where I would recommend that you do your cals. -10, -5, somewhere there. So the other thing that you want to think about for your measurement is something called the IF bandwidth, right? So if you look at a network analyzer architecture, it's effectively a heterodyne receiver, right? So you down convert into a network into a narrow receiver. You have a source, and what you do is you sweep the LO and the source kind of in parallel, so that you do your swept frequency measurement. And because you're only looking at the linear response, you know automatically at what frequency you're going to be receiving your signal, right? Because it's a linear device. So what you're doing there is that you can then digitally filter the signal at the output and allow for a much better signal-to-noise ratio, right? That's how you get the really good high dynamic range that's inherent in a network analyzer, is by being able to access a very narrow IF bandwidth. So for antenna measurements, typically you're looking at return loss, right? The main limiting factor for return loss in terms of error terms is actually a term called directivity, and that's basically, if you think about a directional coupler, right? It's effectively the amount of signal leakage, so the isolation, right, in the coupler, relative to the amount of reflected signal that you're going to measure, right? And in most network analyzers, this is after calibration about -43 dBm, right? So if you're measuring a return loss on an antenna that's better than -43, you're within the uncertainty of the measurement itself. So most people don't try to look for an antenna that's better matched than 43 dBm, 43 dB, right? So that's just something to keep in mind. If you're looking at the transmission, if you're looking at gain, so is it about 50% antennas, 50% filters and stuff like that, or is there a different ratio? Is it 90% antennas that you guys are going to be using?
So far, they're preferring for working on antennas.
Okay.
Probably will cover in future more topics as long as
As
Also
your
two ports.
curriculum. Yeah.
2 ports, last one.
Yeah. So two-port networks, so for example, like a cable or something like that is something that you can do. One of the interesting measurements that we can do is also just to take a look at a two-port measurement, and we can actually go through that fairly quickly. and I can show you kind of what I mean by even on the best day, you're not going to have a really good measurement of the cable. So let me kind of give you a quick demonstration of that, right? So if you So what I'm going to do is I'm going to actually do my calibration. I'm actually going to do the calibration right at the instrument ports. So this means that it's going to be fully calibrated there. You know, because it's within 13.5.
Just I have two questions regarding the calibration. If we change the power level
Yes.
or the frequency span after the calibration, we have to recalibrate, or is that
So if you change the IF bandwidth, the power level, the frequency span is an exception. I'll talk a little bit about how that works. But if you change either of those two, you should not have to redo your calibration. And I'll show you kind of how that works. So what I'll do is I'm going to actually do my, you'll see under my IF bandwidth, it's usually by default when you start it up to 100 kilohertz to optimize the measurement speed. So we're doing the full span from 10 megahertz to 13.5 gigs to and you know we're doing 201 points, and you can see if I go to sweep timing, I can see this takes about 1 millisecond to do the sweep, right? So very, very quick. But if I go to my averaging bandwidth and change the IF bandwidth, and I say I want to actually improve my accuracy, so I'm going to use 1 kilohertz, then I go back and take a look at, well, what happened to the sweep timing? It's gone up to 185 milliseconds, right? So it's gone up because I reduced the IF bandwidth by a factor of 100. My sweep time's gone up by a factor of 100, right? So it's kind of direct link, but this is still, very, very fast. 100 milliseconds for a measurement is pretty good, right?
Yeah.
So, and if you're doing a narrower span in the full bandwidth, that can be faster.
So it will not increase the number of points?
It will not increase the number of points, but at each frequency point, what it does is it digitally filters the measurement more, rejects the noise out of the measurement, right? Because you're only looking at a certain, remember on the receiver side, you're just looking at the received signal within a certain bandwidth. If you narrow the filter that you're using, your signal to noise ratio is going to get better because the signal is the same. And what you're doing is by reducing the bandwidth, right? The noise of the receiver is flat with frequency. We can assume it is. And so as we reduce the bandwidth by a factor of 100, we've improved our signal to noise ratio by 20 dB effectively by doing this. What this does is it will lower your measurement uncertainty, right? So the better your signal to noise ratio is, the better the measurement uncertainty will be. This is really important, more so when you're looking at filters. So if you're looking at the out-of-band rejection of a filter, sometimes you want to measure 60 dB of rejection, right? If you want 60 dB of rejection and you want to know within 0.1 dB of uncertainty, there's a very nice chart that you can look at that details the signal-to-noise ratio that you need relative to the uncertainty of the measurement. And it says about 0.1 dB is relative to 29 dB of signal-to-noise ratio. So we just said 60 dB plus 29 dB of signal-to-noise ratio. That means I need 89 dB of dynamic range, right? So that's why we would use this narrower IF bandwidth, because we want to make sure that we have really good dynamic range in our measurement. So let's talk a little bit about the calibration, right? So when you use the cal, all you have to do is just go cal, so you hit that button there, and then what you can do is, you'll see there's basic cal, but I always recommend that you use the smart cal, okay? So just kind of maybe back up because I went a little too fast there. So under other cals, smart cal, okay? There's I'll talk a little bit about one of the other calibrations that you may want to use if you're looking at multiple measurements. But for now, what we're going to do is we're going to just do a 2-port measurement. We're going to say that, remember here what it says is what is the device under test, right? So not Now what's the gender of the network analyzer ports or the cable ports? What's the device under test? So I'm going to measure the cable, and what I'm going to say is that my device under test is male-male, right? So 3.5 male to 3.5 male. It automatically detects the eCal and goes, that's the one that you want to use, and now it's going to ask me to do some measurements. So the really nice thing about a male-female eCal is it gives you full flexibility in terms of what kind of devices that you want to measure. So if your device is insertable, so that means it has one male port, one female port, you can easily calibrate that. And I guess the only other thing that I want to talk to you guys about is this. Have you guys used a torque wrench before? So if you're typically used to using BNC connectors, BNC just plug into each other and you're done, right? So there's nothing really complicated about that. With the SMA and the higher frequency connectors, there's a specified torque, and this is just basically so that the pin depth and when you make a male-female connection is always repeatable, right? So that no matter who's connecting the cables, it's always done at the same depth, so that it doesn't matter how strong you are, because maybe my fingers are stronger than somebody else's, and so we're going to get different connections. Let's just make sure that it's repeatable. So it's not to make it as tight as possible, it's just to make it repeatable. And so what we do is we apply a known torque, which is basically force over distance. You guys have all done physics, so I don't need to explain that to you. But there's a right way to use this. So what we want to do is we want to grab it past this notch over here. And what we want to do here is just tighten until the wrench starts to break, and then we're done. Okay? So we do not keep tightening until it fully breaks. We start seeing the break and we stop. And then what we'll do is we'll hit measure. So it says, for example, right here, port 1 to the eCal. So it's fairly straightforward. There's no issues, and it'll do those measurements.
So you do not need to connect the DUT?
So we're just doing the calibration portion right now.
Okay.
Eventually, like I said, the DUT is going to be the cable, just so I can show you guys a concept, and then afterwards we'll talk about why. So the really nice thing about using an eCal, if you've done calibrations with a mechanical calibration kit, you have to do short, open, load, and then you have to do a through. So it's a lot of different standards. It's a lot of different wear and tear. You have to make sure that you do them in a certain order. Sometimes you forget to do one, or you connect the open when you should connect the short. None of that's there, and it provides some level of, I'll call it, certainty for you, because so right now it says connect port 2 to the eCal. If I click measure, one of the things that is enabled by default on the eCal is auto orientation. So it will sense how the eCal is oriented and will compensate appropriately for that. But you'll see it popped up in error. It says electronic cal unable to orient eCal module, and it brings up the same instruction. This is because it went to port 2, changed what was going on in the eCal, because remember, it's electronic standards, and said, hey, I'm not seeing a change in the measurement that I'm seeing on port 2. You haven't connected it properly. So this can give you some level of confidence in the fact that if you make a mistake, it's not fully, mistake-free and mistake-proof, but it gives you a really good way to make sure that you can verify some of the issues before you go through the entire calibration. Because if you've gone through the mechanical calibration, if you make that mistake, you don't realize it until the very end of the calibration, right? Okay.
And, how frequent we should do the calibration of these equipments?
Okay, so how frequently should we do calibration, right? So this again depends on a number of things. So this is what my recommendation would be to you in general. If you change any of the key measurement settings, like, so actually I needed to talk to you about frequency, right? So for frequency, if I narrow the span, let's say for example I pick a frequency point every 10 megahertz, just as an example, right? And I narrow the span of my measurement after doing calibration. So let's say for example I do 1,350 points between 10 megahertz and 13.5 gigahertz. So I had 1,350. I narrow the span, and I now use 350 points, and it's still every 10 megahertz. It's okay to not change the calibration in that case. The reason is because I've calibrated at exactly the same frequency points as I have before. If I don't do that, and I change the span, and I don't keep the frequency spacing consistent, what happens now is the calibration is going to be interpolated, because I have a calibration at certain frequency points. I'm now asking it to measure at different frequencies, so it's going to try to interpolate the calibration. It doesn't necessarily mean that calibration is not valid, it's just not as good as it would be if I had done the calibration at the right points. So it depends on the accuracy that you want to use for your measurement, right? So if you know you're going to do a very wide measurement, and then you might want to narrow down, so maybe you're looking at an antenna and you want to say it's somewhere between 1.5 and 2 gigs, and then I say, okay, now I know it's around 1770, and I should narrow down and look at maybe 100 megahertz of bandwidth because that's what I designed. Then I can do that as long as I started with a lot of points. It's okay as long as I keep that frequency spacing consistent, right? If I change the frequency spacing, I'm going to get this interpolated calibration. And sometimes if you don't use enough points, right, or you use too many points, it can cause some issues that way. So I'm going to do the measurement here. It's going to change through the different loads. And now it's going to ask me for the last step. So one of the really nice things about the calibration algorithms that we have is the default calibration algorithm within Keysight is something called an unknown through. So rather than, if you've done it with a mechanical calibration kit, typically what you have to do is you have to use a specific through as part of that calibration kit. And the main issue with that is it has to always be that particular through. It has to have a certain fixed response. It has to be well characterized, and if you use something different, it'll change. So for the unknown through method, all you have to know about the through is that is the approximate length. And I'll talk a little bit about that. It's very coarse in terms of the requirements. So another thing you'll notice is I do 90% by hand, and then the last little bit is just with the torque wrench, right?
It's not too tight, right? Like
it's not as tight as I can. I could probably go tighter with my fingers.
Okay.
But remember, all I'm looking for is repeatability, not how tight can I make the connection.
Mm-hmm.
So then it just says I want to connect these two. You can use an adapter. You can also use this cable. So do measurement. And it'll give me a rough delay. And so you can see it says this is about 3.06 nanoseconds of electrical delay. And if you know the dielectric, the approximate length, you can say, yeah, that sounds about right, or no, that's way off, right? So speed of light is 3 times 10 to the 8 meters per second. So if this is what, a 30 centimeter cable about there? You can look up what it says.
18 or
24 inch. Okay, so it's a 2-foot cable. But you can look at the 24 inches and figure out what that means in terms of length. And you should find that this is fairly good. Of course, because this is a Teflon cable, you have to use the square root of the dielectric constant, right? Again, this just gives you a rough estimate. If you see something here that, like if this said 0.3 nanoseconds, I'd be very surprised and I'd be like, okay, there's something obviously wrong with the measurement. But as long as it's in the rough order of magnitude, that's all I need. So we'll hit OK, and then we can save the calibration as a cal set. So this just saves the calibration data, or I can just go finish and then save up the whole setup. So I have both options there available to me. So I'm just going to go finish for now. And this is actually the response of the cable. So this is why I wanted to show you guys some different things here is under trace. So right now I'm measuring S11, I can add a few other traces. Oh, you have the mouse right there, so I'm just going to go over here temporarily, so hopefully not block you. And you can just right-click and add new trace as well. And then it'll tell you, so you can either do it from the front key or you can use the mouse. And if you do new trace here, it says, well, what do you want to measure, right? So did you want to measure maybe S21? And you can hit OK. And now I've got the gain of this cable. And I can see that the reason that this cable is not very good is that probably around, I'd say 10 gigahertz is probably where this cable is rated. Anything beyond that, and I'm really pushing the performance of the cable. So, if I wanted to say, hey, I would like to add a marker here, I can do that very quickly with right-clicking, and I can kind of, again, verify that at about 10 gigahertz, start seeing some of those issues. We're going to put in, actually, let me just go to here and grab this blue trace. And what we're going to do is we're going to change the measurement to an S21 measurement, right? So that's our insertion loss, right, for this cable. But instead of just looking at it in the log magnitude, which is, what most people look at when they're looking at a vector network analyzer, we're going to change the format and we're going to go to the phase, right? So you can see kind of this is the phase of the cable, and this is what we call wrap phase. So it's basically always going from between 180 and minus 180, and then it wraps back around. But what I want to show you guys, right, is so this is the S21, but if I change this, right, based on moving this cable, you're going to get a different response, right? So this is why I don't recommend using this quality of cable for, maybe for a couple hundred megahertz, this is okay. But if you're going to anywhere in the gigahertz regime, you need to have really good quality cables, because if the phase of the cable is changing and you want to measure, because you don't want to just say, okay, the antenna has 15 dB return loss. That's good. But you don't just care about VSWR. You'd like to also know what the exact impedance, right, in terms of on the Smith chart. Where is this? So I can match it better. Well, guess what? If you have bad phase issues, you're never going to be able to do your matching correctly, right? So this is why you need to have really, really good phase stability in your cables. And if you take a look at the network analyzer, this is like a very key spec for the cables that you would want to connect here. And what that does is that as you bend the cables and you come back to a certain position, it does not vary. So very good cables will change like maybe 1 degree over 26.5 gigahertz as you bend it, really, really tightly. Like all I did here was just, kind of do this, and I can see it's. And again, you have to think about what the scale is. This is 180 degrees, or 45 degrees per division. So this is changing 30 degrees based on me flexing the cable like this. 30 degrees on the Smith chart, no way you're going to match, right? So again, it may work for a few hundred megahertz, definitely not going to work for 3 gigahertz, right? So it depends on where you guys are going to do your measurements. BNC is way worse. So that's just something I'll tell you up front. I've tried to do this to show a customer with this with BNC, because they're like, oh, I'm just going to build some BNC antennas. We used SMA to BNC adapters on the front of the network analyzer, and then we connected a BNC cable. We just bent the cable like this, and then we went back to the antenna, and it didn't even go back to the same place because the cable varied so much. So there are some people who make a BNC calibration standard, mechanical, but I just would never tell anybody to ever use BNC for impedance matching. It's not reliable, okay?
So when we are looking into cable, we have to look into
It's a parameter called phase stability, okay? And if somebody says they make a network analyzer cable, so that there's a couple companies, there's a Japanese company called Junkosha that makes very good cables. There's another company called Gore that makes very good cables as well. They're out of the States. They make the ones in the F-35 fighter plane for the radar system, so they're very good. And there's another company called Mori Microwave. These are kind of the 3 big players. There's also some German companies as well called Huber and Tuner or Rosenbergers. And I think you can find some of the Rosenberger cables on DigiKey as well. But you need to make sure you're using really good cables, because you can get cheap cables from DigiKey and they're fine for some applications. But if you're working, like I said, anything above that 1 gigahertz is where you really need to be careful. Okay.
So for this cable, we can work till 3 giga usage.
Yeah, I mean, it depends on what you're doing, right? If it's for an educational lab, it's fine. If you guys are trying to publish a PhD thesis on this, I wouldn't use it, right? So it's kind of a what are you trying to do with this? If you're trying to look at the is there a filter there? You know, what's the average group delay of this filter? And it's an undergraduate lab. This is going to be fine, right? You can talk about that. You can even show it to students and say, okay, measure the response of this cable. It's kind of an interesting experiment. But it all depends on sort of, like I said, where's your application of this? Are you guys using this for the PhD, you know, this is my thesis measurement, or is this and I'm going to publish this, or is this for teaching a student the basic concept? So different applications. Are you guys going to be using that with a probe station?
Yes, we do.
Right, so the longer your cables are,
Yes.
the more sensitive they're going to be to these phase measurements, right? So that's where you really want to be careful with this. Okay, so we have that.
Just, I have a question.
Yeah.
If we connect the cable and then we calibrate, it will not compensate for that one?
So it will not, and I can show you, again, we can do a 1-port calibration with this, and I can measure the return loss of the network analyzer just of itself. Bend the cable, come back, and I'll measure a completely different return loss. The magnitude might be similar, it might be very close. It also depends on the accuracy, right? So let's be honest here. So let's just kind of get rid of some of these traces. So if I go to here and I go to auto scale, right? Like what's the level of accuracy you guys need for your measurements? Are you trying to find 0.1 dB accuracy, or are you just going to say, you know, as long as it's roughly within, you know, 1 dB, I don't really care, right? It all really, really depends on what you're trying to do. Because, you know, if I go in here, what I'm going to do is I'm going to just change my scale on this trace here. So this is trace 1, trace 3, so I'm going to change the scale. And we'll go in and change the reference level. Just here. And so I'm at ½ dB, but you know, so again, depending on where I am, right? So like this is the halfway point roughly. So this is 6 gigahertz. So if this is I can get it to change by 3 dB by just moving the cable. And you know, here actually let me do even better. Let me go to data to memory. So I have this in the memory. I'm going to go display data and memory. Okay, so if I bend this and then I go back to it, I may not end up where I am, right? So that's the thing, is if I do a calibration at a certain position and I come back, right?
So how did you save? So how did you save?
Oh, so I went to under math, data to memory, and then I went display data and memory. So if I bend the cable in a certain position to do the calibration, and then I bend it a different way to go do my measurement, and now I've changed the response of the cable, and the cable's not settling back to where it is, it means my measurement's going to be completely unreliable, right? Again, depends on the accuracy that I want, right? So maybe if I look at the low frequency, it's not changing that much, right? So if I put some markers on here, just to give you guys some rough ideas, and let's go. So anything below, I'd say like 1.4 gigahertz, probably okay. But if I go and say, okay, I measured it here, and I come back, right? Like this is at that 8 to 10 gigahertz. Like I'm looking at sort of 2 or 3 divisions depending on where I position the cable, right? So that means that that's basically like 1 to 1.5 dB difference, and that could be, you having a really good project for your thesis to you having a completely unreliable design, right? So, hey, this doesn't meet what I designed in ADS. Why is that not working? Well, because your cables are not good, right? And you bent them a certain way. So if you want to eliminate that level of uncertainty, now again, if it's in a teaching lab and you say, okay, the filter has a response, the bandpass is roughly here, somebody's going to get the concept. If you're doing your doctoral thesis on this, definitely not the right way to go. So that's kind of, like I said, what's the level of accuracy you need. If this is just for teaching, for demonstration, to get a rough idea, does this device even work? This is fine.
So use maybe this one. It should be better.
So this should be a better cable, right? So let's take a look at this.
Is that 3.5 mm?
So this is still 3.5. Oh, you're getting another wrench. So did this come with a different system, or?
Yeah, it's 4200, the semiconductor parameter analyzer.
Okay, so this came for your.
Keysight.
Oh, the Keysight one.
Yeah.
And this is for doing pulse measurements, so using the Keysight that you guys do for.
They're mainly doing like semiconductor characterizations, like IV characteristics.
Yeah. So does this act as a bias cable, or is this more for RF, or what are you using this for?
From RF, I guess. Calibration.
Now, so this is. I can tighten it to make sure that we're getting the right. Yeah, this cable's got not a very good match. I can see that right away.
And different impedance level, or
The return loss of the cables, yeah, it's not very good. So you can see, like, you're getting roughly about 2.5 dB of insertion, but and you're getting a lot of ripple. So that means that there's a standing wave kind of going on. It could be in the connector or something like that. But this is a good tool to have. I mean, this is not what I'd recommend that you use to check your cables, but this is a good way to do that as well. Are the cables that I'm getting from manufacturer X, Y, Z, are they actually working, right? So what you want to see is flat response, and it could also be the SMA bullets that we're using are not the best, right? So what we recommend typically is either when you mount this, you keep kind of your network analyzer cables fixed on it, and they're either female to male, or you get some high quality 3.5 millimeter, those air dielectric ones, just for the network analyzer, because they're going to make sure that the limiting factor of your measurement is not everything that's going to connect to the DUT. It's the DUT is going to be really what you want to measure. You don't want to have poor SWR in the bullet, because if the bullet has just is not very good quality and has bad SWR, you could have repeatability issues even there. So again, I'm zooming in a lot here, so if you just want to get like what's the rough response of this cable, well, you can say, yeah, I mean, this cable has about 2.5 dB of insertion loss. Again, if I go back and look at it, this is actually the S11, right? So this is actually a minus 10 dB of return loss. So it's not the worst, right? That's the loss of the cable, but the insertion loss of this cable, right? If I go back to
What is this measurement?
oh, this is just the
No, that's the safe one. The other one below.
This is the insertion loss of this cable. So it's actually really poor at higher frequencies, because it's probably made for DC. It's probably made for shielded DC is what I would guess for this cable. So anything after even 6 gigahertz, this cable is not good.
That's why it has like a gain or something.
It doesn't have gain, it's just a different scale. So here this is the scale.
Oh, okay.
So you can have different scales here. That's just something to be aware of. One of the things that you can do if you want to be able to kind of separate this is, so this is a little bit easier to do with the mouse, is you can drag this and you can have 2 separate plots like that.
So we cannot change the y-axis, one on the right and the other one.
No, you can't do that. It'll be whichever one is active will be the one displayed on the left, or you can separate them like this. The other thing you can do is create something like, in Excel how you have different tabs. You can create multiple tabs on this as well. So if you go under Instrument, response here, and under response. I'm having a little bit trouble finding it here. Can I actually check one thing really quick as well? I forgot to look at before I started. So, if you go under System, you go under Service, Help About Network Analyzer. This also tells you the version of the firmware you're using. So you guys are using a really old version of the firmware. I think we're on 13.5 right now. So this can be found, and I'll give you the website right now. It's NA, which stands for Network Analyzer, .support.keysight.com. And at that website, it gives you actually access to the help file. So when I press help here, sorry if I don't have this active, if I press help here, this little help file that pops up that's searchable, that allows you to look at, it's context dependent, so because I press system last, that's the one that shows up. But if I went back to sort of the contents, and I went back to the top here and just said, okay, under home, you can see the quick start, you have setup, you have access to the to how to analyze the data, all of that. And it also actually shows you through the calibration routines as well, if you're interested. This help file is downloadable at na.support.keysight.com. You can download that on your computer. It's fully searchable, just like the application here.
From here, or you can also download from the website.
You can, yeah, that website that I just gave you. You can download this exact help file
as a PDF.
So you can get it as one of two things. You can either just go to the web help, so it's just the website that runs all this, allows you to Google search it, or there's something called a .chm file, and what it is it's basically like you can think about it like a mini application.
Yeah.
And so you should be able to run that on any Windows machine. I don't know if it works on Apple. I haven't tried that, but you can say, okay, I want to take a look at that noise figure application, right? So you can go in here and say, I want to take a look at this noise figure option. Tell me how this works, and it actually gives you noise figure theory, how to set up a noise figure measurement. All of that is there, and it's just click on, say for example, okay, how to configure your hardware, how to calibrate it. What are the X parameters for noise figure?
So they describe all the steps, how to do this.
Exactly.
Okay.
And it also gives you like some theory as well as to how the measurement science of the instrument works.
By the way, do you have any hard copy of these manuals or kind of this? If you have one copy with this machine, so you can keep here if students wants to.
Yeah, we don't really do hard copies anymore. We used to give out big binders. We just found that it killed a lot of trees and nobody really used the hard copies. So we either have downloadable PDFs or the web help is something that, again, you can just share the link to somebody, or you can download it on your machine. So every student can download it on their machine if they want to. But I would recommend that you upgrade the firmware as soon as you can.
So how to upgrade the firmware? So I go to the support websites. And
yeah, and then you'll see it says latest firmware versions for PNA. You'll download it. It'll be probably about 600 megs. You'll put it on a USB stick. You put it in here, copy it over to the desktop, or you can save it on a file. You go, file, exit application, right? So close the application. Double click on that. Do it hopefully when it's not thunderstorming outside, because what it will do is it doesn't just copy some software and install it here. What it does is that inside the network analyzer there's some FPGAs, and so what it'll do is it'll actually reprogram the FPGAs when it does that. So that's why I would say don't do it during any chance that there's a power outage, because if it goes down in the middle of reprogramming the FPGAs, it can be not so good to try to recover the system. It's very painful. It is doable. It's not as easy as it should be.
And what is the latest version number? Like you said, it's 13 point something.
I think it's 13.5. It says if you go to latest, it'll tell you this is the latest available.
Okay.
But yeah, this is like a few versions behind, which is why it looks a little bit different than what I was working with this morning.
This is not on a network, the machine.
I don't think this machine is on a network right now, right?
No, it's not.
No,
It can be.
you can, and then from there you can actually update the firmware directly on the instrument. So it'll download it if you put a network. There's something in here that says update firmware. It'll download the firmware and then say, okay, closing all measurements. Are you ready to install? And it'll do all of that. Some people don't like to put their machine on the network because of the IT security policies. It's entirely up to you guys how that works within York.
We can also remotely access this, or no?
You can. So you can run Type VNC on this, which is what most people do, or you can use remote desktop. So that way, if somebody's in a lab and you're trying to explain a measurement to somebody in a different building, you can just say, hey, here's the IP address of the machine. You can remote desktop or use Type VNC, so you can both share it. Perfectly valid.
Okay.
Yeah. The one thing I wouldn't recommend is like, I mean, it is a full PC, but I wouldn't put like MATLAB or any really intensively computational application on here. Like ADS, for example, if you're trying to do a 3D simulation. Yes, technically it could work, but there's not a lot of RAM on this machine, right? Because it doesn't need to. A lot of the post-processing runs on the FPGAs, right? So it's kind of like using GPU acceleration. So it's not, except it's done in the FPGA. So that's why I said this. You'll really make sure that you're not really worrying too much about the extra software. Another kind of cool thing that you can do with this is, I don't know, maybe you're doing something a little different, and you may want to not just display the S parameter data, but you might want to put it through an equation, right? Maybe sorry. Like efficiency is a very good example, right? So you can measure the DC power at the same time, and you can say, take this gain and then actually divide that by the DC power consumption, right? Or the output power. So you can actually go under the math functionality here, under analysis. There's something called equation editor. So you see that? So you can launch this, and you can actually use this to select a full equation. So you can say S21 times S12 with the cosine, sine, all the basic math functions that you have access to. You can look at just the complex. You can do exponentials. You can do the impedance. You can do powers. You have access to, like I said, pretty much a full math suite. And what this does is it'll take whatever you do. You'll call this variable whatever, and you can say plot this. Sorry?
Can we try, I guess, try?
Well,
For example, magnitude of S1 square.
So yeah, so let's go here. See if we can find.
That's nice.
So that's probably the fastest thing. And me trying to do it using touchscreen. I always forget that people have a mouse. So we can go, okay, S21, we can do, should probably, yeah. It gives you like, a little bit, some magnitude of a complex number. And then you said, okay, I want to, so move the backspace one more. Go here and say square, right? There you go. And I can just plot that directly.
You mentioned the power. Can we measure the power as well? Like we show
Correct.
versus frequency?
So under here, right, so we had this. I can get rid of the equation editor. And under measure, so you saw your S parameters. I'll talk a little bit about some of the other things. So the next thing is you're going to have is receivers, right? So using your power sensor that you have here, you can do something called a source power calibration. What this does is it gives you absolute power at the end of your cables, at the end of your fixturing, right? So if you did this with a probe station, say for example, this is a very typical application, you have an on-wafer device, you want to expose it to a very specific amount of power because it's an active device, then what you can do is you can do the calibration. Obviously this will be coaxial, so do your gas parameter calibration with the eCal, you'll do your power calibration with the power sensor, and then what it will do is it will require you to do your on-wafer cal, right? So usually maybe you guys do a TRL cal on wafer. Is that something, has anybody done on-wafer stuff here?
Not yet.
Not yet? But you, what kind of probe? Is this a cascade or is this?
No, two separate. One is for RF probe, one is for DC.
Which one is the what?
The right one is the DC and left one is the RF.
So what's the RF one there? What brand is it?
NPI TS 150.
Oh, it's yeah.
NPI.
Yeah. So, so they might have like their own standards or something like that. You should have like a calibration substrate.
Yeah, they have the regular.
Right. So you can. I'll talk actually. You have. They come with a little bit of piece. So sometimes if we don't give you the cost center, we don't give you a sheet for they might have their own like application around this. I don't know specifically how it because I'm not an expert in air systems. I haven't worked with them a lot. But I'll kind of give you a feeling for so sometimes they might give you something that has all the CAL standards in terms of factors. But we're just going to go back to the network analyzer first. So if you look at here, this is probably but under the so you can do the power, and what you have to think about is the architecture. So if you go to the block diagram of this, the way that we talk about the receivers is that we talk about the reference receivers. So that's the R receivers. So the reference at port 1, it's called R1. For the reference at port 2, it's called R2. And then we talk about the measurement receiver. So that's A is the measurement receiver on port 1. So for example, if I'm doing a measurement where I'm stimulating from port 1, the A receiver would be measuring the reflected signal, right? Because the source is at port 1, and I get a sample of the signal in R1, and I get the output signal at the B receiver on port 2, but the A receiver, which is back at port 1, is measuring the reflected signal coming off the device. So if I put in A, what it does is it tells me what receiver would you like to measure, denominator, so you can put it as just the receiver or you can do a ratio, right? And then it also has the where do you want to put the source. So if I do A at port 1, I'm measuring the reflected signal. But I can do something where I do A and I put the source at port 2, and if I do this, what I'm now measuring is, and again, I would just I can go into scale and just auto scale this. What I'm measuring is the power that's transmitted when the source is at port 2 going into port 1, right? So remember, I'm setting that, again, this is uncalibrated for the power, right? But if I go into here, I can see that the RF power is -5, and I'm getting roughly, somewhere between -6, and then it's dropping to about, -11 at this frequency, right? And that's just basically the response of this cable over frequency. Also handy feature here, undo. So if you do something wrong, you accidentally do preset the instrument, and you're like, oh no, I wanted to go back to what I had, you can undo, which is nice, right? So this gives you a lot of nice features that way. Okay, so I've covered some of that. I'm trying to think of what else there could be that we might want to talk about. Calibration substrates, right? So under cal, right?
So is there a specific for power calibration?
There is, right? So under other cals, you can see here there's source power cal, and this will calibrate the source power of the network analyzer, which will in turn be used as a reference to calibrate the receiver powers, right? Because if we know what the source is, we can figure out what the receiver powers are. But under you see here cal sets and cal kits. So under cal kits, right, you can see it's looking at the eCal, and it has a number of different default mechanical cal kits that Keysight makes. But you can import a cal. So for example, if they gave you a USB stick saying here's what the calibration standards are for that MPI cal kit, you can import it into here, and then when you're doing your probe measurements, it'll say, okay, I know you're using the Titan probes on your MPI probe station. Give me the through, give me the reflect, give me the line, give me the offset line, or whatever it's going to be in terms of the standards. But I'll guide you through that calibration based on the way that you define the calibration standards in that cal kit. So that gives you a way to, so for example, if you're making your own cal kit for a particular substrate, because their cal kit may work very well for the MPI substrate, but you may be using a substrate because you're working on exotic materials. I don't know what you guys do here. But there might be somebody saying, I'm doing some cool, niobium superconducting antennas. I don't know, right? And so I need a particular calibration substrate for niobium, and that is not going to be whatever they have there, right? That's I don't know, maybe a FR4 or something like that type calculus.
The measurement that you showed us just now, you set the power and then we saw the insertion loss, right?
Yeah.
What's the difference between that and the S21, for example? Is it the same?
So again,
It's the same thing, right?
so let me grab this and put it here, right? So this is the way I define A21. So let's go here and let's actually go measure. Let's go back to receivers. You see I have S11 over there. So what I'm going to do is I'm going to say, look, I can do R1. Actually, no, I should do this the other way. I should do A over R1 when the source is at port 1. If I define it this way,
What is R1, sir?
so R1 is the reference receiver. So that's the sample of the signal, right? It's only usually valid for whichever port the source is on. So if you measure R2 when the source is on port 1, you're not going to really get a signal other than the leakage signal. So it's going to be very, very small. But let's just show you this. And if I go to, so this is a 10 dB scale, so let me go back to another 10 dB. My reference level is going to be okay. So because I don't have a power correction, they're a little bit different, but if I had a power count, I would see exactly the same thing. Right, so now I've done a ratio power measurement, which is effectively an S parameter measurement, but you'll see it says here, if you're on this trace, it says no core, which means no correction. It's because I did not do a power calibration. If I go to the S11 measurement, it says C delta 2 port. And I can just close this window because I don't have anything there. And you can see here it says C delta 2 port, and that's because I did a 2-port calibration. And I think I might have changed the resolution bandwidth, sorry, the IF bandwidth or something. So if I change any of the parameters, it'll pop up with a little delta here, but otherwise it'll be exactly the same.
What the power calibration does? Like I have not done it. Like I
So
have no idea. Because
normally when you do a VNA measurement, when you say I want to measure at minus 10 dBm, that's minus 10 at the port. If you have, say for example, your probe station, or you have you're going into an anechoic chamber, and you say I want minus 10 dBm at the antenna, it will give you calibrated power at the end of the cable. And it will give it to you within the uncertainty of the power sensor. Because typically this is like, it's a good guess, but it's not, like this has, 0.05 dB of uncertainty in terms of the measurements. So you'll transfer this uncertainty into here, right? So you're going to get a really, really accurate power measurement, not just it's a pretty good power measurement.
Can I ask a question? Like,
Yeah,
for example, let's say I want a power from the VNA,
Yes,
and then I have some circuitry in between which is not matched to my circuit.
correct.
Then I can use the power meter to do
To
that.
do the calibration, yes. So for example, let's say you've got a circuit that you have and it has a tunable LC, right? Let's say that's what it is, right?
I have it, like for example, a VNA, and
Yes.
then I have some sort of
Balun?
yes,
Okay, yeah.
differential.
Yeah.
And then I have my design under test with some load.
Yeah.
Then I want the power to be exactly here that my circuit is seeing.
Correct. So if you do the calibration at the end of the balun, you'll be fully there. So if you want to do differential though, here's the better way to do it. I'll show you how to do it because you're doing a differential return loss. You're not doing a differential insertion loss, right? So you say I want to do differential measurements. Okay. So remember when we did here and we said measure? You know how default it goes to S parameter? There's also this balance thing. And so all you do here is you say, well, let me see what the topology is. So we're going to change. And you can see this is a balanced device with port 1 at the positive, port 2 at the negative. So you can connect it directly to this, and it will give you SDD11, which is what you typically want. Right? So you can do your differential, your common mode, the differential transfer, your differential to common mode, and your common to common.
Even this is good for coils, right?
Yeah.
If I want to do the differential coil.
If you want to do differential coil, you can get all the parameters for your insertion loss right here.
So if it's single-ended, then I can ground the anthem.
Yeah, as long as you have some very good 50 ohm loads. Make sure you get really good ones, not cheap, because otherwise you'll get transfer back and forth and it won't be good.
But the impedance of the coil might not be like 50 ohms.
Yeah, so I guess you need to make sure they're well, whatever the coil is, you need to have it well terminated. That's why sometimes it's nice to have a 4-port network analyzer, because then you can connect and you can actually. So if you've ever done differential measurements, right? Like again, I can get 4 differential parameters with 1 set of differential ports and 4 sort of single-ended S parameters, right? If I have a true 4-port network analyzer, I can get all 16 differential parameters and 16 single-ended S parameters at the same time. There is an application, like software that can run on a PC. It's called our physical layer test system, and that can allow you to do multiple S parameter measurements and extract the full. So you would do 4 2-port measurements to get a full 4-port, because you need to do all the crosstalk terms and everything. So it takes a little bit longer, but you can extract the full, as long as your device is passive, right? Because if it's active, you need to truly stimulate differentially. Otherwise, you're not going to get the true S parameters. But that's something where you can extract the full 16 S parameters based on multiple 2-port S parameters.
You mean like if we have one transmitter multiple receivers, we can do it with this. Or?
Yeah, it works really well on the device is 50 ohms because then you put 50 ohm loads on there and you move around which test ports you're doing. If it's not 50 ohms, it's a little bit trickier because you still need to terminate, but now your termination uncertainty is a little up in the air because every time that the termination is not good, it adds more uncertainty to the measurement, right? So that's what I would just kind of caution you with.
So basically, you cannot do with this because it's just 2 ports, right?
You can do single-ended differential. Sorry, you can do one-port differential, but you can't do 2-port differential measurements with this if it's active. I mean, if it's 50 ohm and it's passive, you can kind of do it because you can do those multiple measurements and build up that S-parameter matrix, but it's a little bit more complicated. There's actually an application in ADS to take 4 2-port S-parameter matrices and build that into a 4-port S-parameter matrix. It exists in ADS. It's just like if you said if your device is not 50 ohms, then how do you terminate it, right? Every single port is going to have a different termination. You need to make really good terminations to make sure you minimize the reflections. It becomes really, really complicated. If your device is 50 ohms, you can just buy really good 50 ohm terminations and then, not have to worry about it. Yeah, so that I think gives you a pretty good idea of this.
Then can you sweep power?
Absolutely.
For
So
example, to get the intermodulation or P1 dB compression.
yes, to some extent. So this will give you the gain curve, and you can then you can look at the data and post-process it to get P1 dB, or put a marker and say find the delta to this marker to 1 dB. So there's some ways you can do that. Yeah. So I'll show you.
P out or P in, for example. Power of
Correct. So that's where a source power calibration would be good, because if you want to know what the P1 dB is, you want to know what it is at the device, not what it is at the test port, right? So let's do a very simple case with that. Again, the cal is not going to be very good, but we can go through that, right? So
can you show
Change
us
the cable.
the power calibration?
yes, I'm gonna guide you through that whole calibration process.
Are we doing the other scope today?
No,
That's later on,
it should be tomorrow actually.
tomorrow same time,
Tomorrow 10:30.
tomorrow 10 to.
Yeah, so Tim, sorry, I should have introduced myself at the start, but sure, Jill's half asleep and he usually takes care of the introductions. But I'm your RF and microwave application engineer. So I live out of Waterloo. I did my master's in power amplifier design, validation, and testing. And I work with a number of customers doing that still to this day, as well as full RF subsystems for satellite communications, 5G, and some other medical sensing applications as well. But yes, the infamous Slim Boom Mesa, yes. A couple of years ago, more than a couple now. It's been too long. But the really nice thing about this is that this was the platform that I did. Some of the features that we have on this now are going to simplify your life. If you're going to do amplifier test, there's a lot of the features that you have access to here are available as a free 30-day trial license. So what I would recommend that you do is I'll show you kind of the old way to do it. This is the way I did it back when I was writing my master's defense. But what they did is they made it super easy so that what I had to write lots and lots of code to automate this particular measurement is now you set it up. It takes 30 seconds, to set up and to do the measurement, and probably 29 of that is spent setting up the measurement, and it will give you exactly P1 dB over frequency. You can get the full 2D power over frequency extraction curve to build a model. The way that I did it, it's a little bit more complicated. I'll show you how to do that. Okay. So you can see. So you can see here there's plus trace, plus channel, and the other one there's also plus sheet, but I'll kind of set this up here. So you can see here, this is our typical 10 megahertz to 13.5 gig, but that was at 1 power, right? So if I wanted to do something here, I can do it one of 2 ways actually. So I can create a new channel, So this is a completely different set of stimulus. I can do it at a different power, different frequency. And channels are basically stimulus conditions for your measurement. And you can have up to easily 99 of them on the network analyzer. So you can have a lot of different measurements going at the same time. So you can do 99 different power sweeps. So if you wanted to get that full extraction, where you can do the different frequency sweeps or different power sweeps, and I'll show you kind of how to do that, right? So let's say, for example, you wanted to do a power sweep, right? So we go to sweep, sweep type, over here, and then you can see the default sweep type is linear frequency, but you can say I want a power sweep. And it gives you the number of points. Most of the time when you're doing a power sweep, you probably don't want any more than like 51 points. Really, it's overkill to try to do more than that, but you can. And then, for example, here I can do from -10 to 0, or let's say maybe this is a more interesting amplifier, so let's go from -10 to 0 dBm, right? And I can go to frequency. You'll see it says CW at 1 gigahertz here, but I can say, you know what, this is a 3 gig amplifier.
What is this? CW?
So because it's a power sweep, the source frequency is going to be at one point, right? So under the standard application, right? So this is the S parameter application. You only have one variable that you can sweep, whether it's frequency or power. You can't sweep both at the same time. There's a specific application for characterizing gain compression, and that's called the gain compression application, and that allows you to sweep power and frequency, and it allows you to do it in either way. So you can sweep power over frequency in the sense of, you shift frequency points, you sweep power, you shift frequency points, you sweep power, or you can do it the other way where you keep the power constant, you sweep frequency. So it depends on kind of the sensitivity of your device. Because some devices you don't want to ramp up the power and then shift frequency and then start at a low power again because they have memory effects. So what you can do is you can say, I'll sweep all the frequency at one power, move to the next frequency, go to a different power, and then go back and forth. So that one gives you full access to how you do the 2D sweep. Again, it's available for trial for 30 days. You guys can look at it. And if you're about to do a measurement, I would strongly recommend you do that. But I can do this, so here I did -20 to 0 at this, but say for example, you know what, that's great, but I want to look over a number of different frequencies, right? So I want to do 3, but I want to see if the same amplifier can be used for maybe some other applications, maybe for Wi-Fi. So I'm going to do another power sweep over here, and I'm going to set this again to -20 to 0, and then for frequency over here, we'll set this one to 2.4 gigahertz. You know what? I'm gonna go to this channel. I'm gonna delete this channel because I don't want this one anymore. But I'm gonna add another channel.
So we can have 4 screens at the same time.
You can have as many screens as you want. You can do it. So if you have a big display, because there's a VGA port on the back, there's a mini display port on the back. So you have a nice big display. You put 100 on there, nobody cares, right? The issue is it just gets really small. That's why I said in the new firmware, what we did is we added something called sheets. What that does, it's like tabs in Excel. So you can have and you can actually rename them. So you can say one is, 13.5 gig power sweep, 10 gig power sweep. You can call them whatever you want, and then that gives you an idea. Because here, I don't necessarily I can look at it here and kind of see some of that information, but I don't know which one is which frequency, right? Unless I click on it, right? So it says here CW 2.4, but if I start putting maybe 8 or so of these, I'm going to have a hard time figuring out which one is which, right? So that's where we're going to do that. But I'll just kind of set this up over here, and I'm going to go power again. Actually, sorry, let me go to sweep. So another power sweep over here. And then we're going to do this one maybe I'm interested in seeing if this also works at 5.8 gigahertz for some of the other Wi-Fi application. When we go start, it's minus 20 again, and then frequency is 5.8 gigahertz. So now I have 3 different power sweeps, right? At 3 different frequencies, and I'm going from again minus 20 to 0. I could have used different power levels if I wanted to, if I knew that the amplifier was more sensitive at one frequency band, but each channel is completely independent. Now, what I can do is, okay, how do I calibrate all these, right? So let's put this. And because I'm doing a power sweep, it's probably going to want to do a power calibration as well, and we'll go through how to do that. So again, I would not recommend using these cables for the measurements, but you can. Let's grab 2 of these basic cables. You guys don't have an amplifier or anything here? Yes?
There's some preamplifiers.
What's the gain on them? Do you know? What's the power level?
I'm not sure.
Okay. If we don't know, let's not hook them up because we don't want to do anything too funny. If you have the data sheet next time and you know exactly what you're going to measure.
Minus 20 will accept.
Sorry?
Minus 20.
Well, I'm worried about what the gain is. If the gain is 30 dB,
Okay.
then you might damage the network analyzer. So just to give you an idea, you'll see here, it gives you, there's a plus 30 dBm max, right? And it has a DC offset for the maximum DC damage level as well. So anything more than, I would say 27, you really need to be careful, especially if it's, because it could be fluctuations in your power amplifier, and then you blow up your network analyzer. So if you look at the network analyzer, like compression of its own internal receivers, anything above plus 12, the receiver will be at 0.1 dB compression. So it's still not compressed. It's still going to give you fairly accurate readings. But if you're trying to measure something with a very high, over 10 dBm, so that's 10 milliwatts of output power, I would recommend that you probably start thinking about using an external attenuator. And there's ways that we can calibrate with an attenuator. I'll talk a little bit about that as well. So we've kind of gone on for a little bit of time, but we'll do our cals. And I'm gonna not put a device in here, but what I'm gonna do is I'm gonna treat this as if most of the amplifiers are what they call insertable. So they have like a male input on one side and a female output on the other, usually. Is that what you guys see on yours, or are they female? Okay, so this is going to be our amplifier. We're not going to see anything, but this is an interesting thing. So it's just this, right? But we'll treat it as that, and we'll do the cal. Okay. So what we do is under cal. So you remember last time what I did is I just did smart count, right? And what that does is that calibrates whatever active channel you have. What you can do under other cals here is instead of the smart cal, you can activate something called cal all. What this does is it calibrates any number of channels you want. So under cal all, you'll see it says, okay, channel 1, 2, and 3 are all different standard measurements. They're all 2-port measurements, right? We can go next. It says include power calibration. And it says true. The reason that it defaults to true is because these are power sweeps, so it's going to say you should probably do a power count. Okay? And in order to make sure that I can actually do the power count, we're going to connect our power sensor. So I'm sorry, I forgot your name.
Mansoor.
Mansoor?
Yes.
Can you connect this USB cable to the back of the PNA? Should be a, I don't know if you can see. Do that. There should be some USB ports on the back here.
Oh, I'm using the back USB port, not in the front.
Yeah, so I'll tell you why. I mean, the reason that I like doing the eCal and the other ones at the back, A, is because Generally, they're going to stay with the network analyzer, so there's no point in disconnecting them. And secondly, when you start putting a lot of USB connections in here and you're trying to connect things around the port, the last thing you want to do is accidentally touch something and hit preset or something like that. So for the power meter and the E count, I like using the back ones. That's just personal preference, because there's 4 on the front and then 2 type 2s on the back and then a type 3 as well on the back. So there's lots of USB ports. You can have a lot of different USB devices. So that gives you a lot of flexibility. Okay, so we've got power cal true. It's going to say what do you want to do the power calibration at. So it defaults to -5. We can set it to something else if we want to. But -5 is good enough. And then it's going to say, okay, it's 3.5 male is the default. That's fine as well because we're going to say that the amplifier is female. And then the last part here is the power meter settings, right? So,
sorry, I didn't get to.
oh, for this?
Yes.
So this is asking what type of connections are on the device under test, right? And so they're 3.5 female. For us, this is going to be our amplifier for today. Next time I come in, we'll know what. If you give me the specs of your preamp, we can plan around that and we can do the measurement, right?
I thought maybe you have some sample device we could check that.
I do. I just assumed that you guys were going to have a device that you wanted us to measure together. So we didn't really discuss that ahead of time. But next time, if you guys I have a small amplifier and a small filter as well, so I didn't bring them with me because I just assumed you guys were.
To show some practice.
I can show you guys the actual measurements. We'll measure the bullet for today, but again, if it's not an issue, we can definitely do that. So it's much more interesting than the bullet, but and I'll actually bring the good cables as well, my cables, so you can see the difference between the cables that I'm using versus what you guys are using. So the next thing is the power meter settings, right? So basically I just go into here and I just make sure that I'm on USB, right, because this is a USB power sensor. And I make sure that the model number and the serial number line up. So this is a U8485A. And I look at the serial number in the back, it ends with 0003. So 0003. Okay. This is where it gets a little bit interesting, is I can set the tolerance. So if I want really precise measurements because I'm doing a power amplifier, right, I can actually set this and say I want to be within 0.1. I can also set that, but that might be kind of unrealistic. I can say I want to be within 0.1 dB. That's well within what the accuracy tolerance of the power sensor is, so I can easily meet 0.1 dB.
You just hit enter and the dB comes?
Yeah.
Okay.
Yeah, you don't have to put dB because it's not there. The one thing I might want to do though is just change the number of readings. I typically recommend that if you're going to use a fairly low tolerance, increase the number of readings to about 5. If you do something like 0.05 dB of tolerance, then maybe put in 10 readings. This is the number of readings that the power sensor will take with the source trying to hit that particular power level so that it gets the right power, right? So the tighter the tolerance, the more times you're going to have to iterate to do your readings. You can also use something called a loss table. So for example, if you're going to do high power measurement or something like that, you may want to put an attenuator on the front, or you may need an adapter, right? So for example, maybe your device is a type N, so you might have to put a SMA to N adapter, right, on the unit here. And so you can say this is the loss of that adapter, right? You can do all of that. So there's a number of other features available here. One of them is use multiple sensors. So this is usually when you're doing waveguide. So I don't know if you guys do waveguide antennas, but say for example, you're going to do a power cal and you may want to do, one of your sweeps is for an X-band antenna. Like maybe you have a device that has splitter, and one of them goes to an X-band antenna, the other one goes to a KU, right? And so you want to have different power settings depending on where you're going to measure on your device, and so you may need a waveguide X-band power sensor and a waveguide KU antenna. So you can use multiple power sensors that way as well. The other thing is, if I want to be super accurate, because like this is a male type of connector on the power sensor, and the cable is going to be male, I can't connect the two directly together, right? So I would typically have to use an adapter. I can add an extra step to my calibration process to do match correction for the adapter. So if I'm worried a little bit about the quality of the adapter, I can add this, and I can just click on de-embed adapter, right? This is usually if like you have a cable or like a fairly long kind of adapter. For this, you can just kind of like say, okay, depending again on frequency, right? So because you guys work at fairly low frequencies, I would not worry about this. But if you're saying, I have some customers that work at 40 gigahertz, something like this at 40 gigahertz makes a big difference, right? So I always recommend, to use that for 40 gigahertz, to use that de-embed adapter feature. For 1 gigahertz in this adapter, it's probably going to be 0.05 dB difference. So again, all depends on the accuracy you want to use. So this can give you an idea. So what you can see here is we're going to do 200 points. And these are the number of calibrations we're going to do from 2.4 to 5.8. We're going to do 5.8 to 5.8 for one of our measurements, from 3 to 3, from 2.4 to 2.4 in terms of the frequency. Now these are all power sweeps, so that makes sense. And these are the different, all the different channels that we're using all have the same frequency as the start and stop, right? Because it's a power sweep.
So we can increase that one if we want to change the frequency, for example. We want the power to have different frequencies.
Yeah, so I created 3. You could create as many as you want, like up to 99. Okay. So the next thing it says is on port 1, and again, just want to make sure nice and relatively tight. So it says I'd like to measure the power at 0 dBm. So it defaults to 0 dBm for a very good reason. So actually, can I get you to do the connection? So if you, have you guys used a power sensor before? No? Okay. So most power sensors, if they come with an external power meter, this one here has its own little calibration because it's USB, so I'll just hold on to that, are calibrated at 0 dBm, right? Just so you know. So that's the reason why it prefers to do the calibration at 0, but you are free to do it at any power level you want. So there we go. We're done. We measured 0 dBm across 3 frequency points. So this part of the cal is done. That's quick. I don't know why it's talking so much. It seems like the USB connection might be loose or something.
So that's the power sensor, right?
That's the power sensor. Okay, so the next step is fairly straightforward. Connect port 1 of the eCal to, port 1 of the network analyzer to the eCal. So we did that as part of our standard S parameter calibration. So just You guys buy a spectrum analyzer as well? Or no.
Yes, we have.
From us?
No, it's from SRS.
Okay.
Will you also show us the other calibration module is the same or it's different?
It's very similar. Yeah, so it works exactly the same.
Why do you have two?
Why do you have two? Okay, so that'll come up when we talk about noise figure. So for noise figure measurements, how familiar are you guys with noise figure measurements, just out of curiosity? Not at all? Okay. So, typically when you're measuring noise figure, you're either looking at a converter or a LNA or part of a LNA and converter chain, right? Sometimes you may look at a noise figure of an antenna, which is maybe something you guys have heard of, but that's a little bit of a different measurement. You don't typically do that using a network analyzer, and I'll talk a little bit about why. Actually, I'll also send you guys, I'll send the professor a link and hopefully he'll distribute it to you guys. I have a 1-hour webcast talking about noise figure measurements and noise figure techniques. And it's not just done by somebody else at the company, it was actually done by me. So,
Again, we need to recalibrate.
yes, because we changed the settings, right? So, I'm going to do that.
But no need for the two.
So, yeah, we still need to do the third. One thing I don't see in your lab is, do you guys have an adjustable wrench in here? If not, it's fine, I got it. I would, okay, so I'll give you guys a recommendation as well. Just because of the, you're going to get a lot of different connectors like this where you want to use two wrenches. And you'll find that like every manufacturer's adapters have a slightly different diameter here. So what I'd recommend that you get is a very nice small adjustable wrench that you can use to be the fixed part, and then you use the torque wrench as the different part for tightening the connectors, right? So then we just need an adapter for this. Right. So yes, for noise figure, that's what I was talking about. I was like, where was I? I tend to ramble on a little bit. So when you're doing noise figure measurements, you're typically dealing with receiver, and if you're doing something where, this is especially important when you're doing things on wafer, which it sounds like you guys are going to do more and more. What's the impedance of your device on wafer? Is it going to be 50 ohms? Ideally, it'd be 50 ohms, right? But it's not always going to be 50 ohms. So the issue with that is that if you take a look at the definition of noise figure, it is the added noise power of the device referred to 50 ohms. So one of the ways that you do that is that if you do it sort of with the typical method where you're just measuring with a spectrum analyzer. So actually, it's fine. We can keep this here. So just finish it. And this is a very short adapter, so you can see it's much shorter. You can see the input match, right? is, it's constant with power, which makes sense, right? That's a good thing, right?
So we want the flat responses.
Well, it's a single frequency. So this is a passive device. Its response should not change based on power. And what's really good is that you can see at, at 2.4, you're getting roughly minus 40. At, I think this is the 3 gigahertz one, you're getting around minus 50, and then at higher frequency, maybe at 5.8, you're getting roughly minus 30. So you may get some variation, but most of the noise down here, like you'll notice it's much noisier down here than it is up here, is because at lower power, you're going to get more noise in the measurement, right? At minus 20, if you have minus 40 dB of reflection, and you come back, you're already at minus 60, and then you go through a coupler to get into the receiver. Now you're at minus 70, so you're getting into kind of the noise floor of the measurement, right? In terms of the capability of the measurement. Remember what I said about the best corrected match that we can expect, right? It was around 43, sometimes 47. In some cases, over frequency, on a really good day, if you take a look at what happens when you have sort of the optimal settings, and so all of this is in the data sheet for the PNA, based on the eCal you're using, you can get down to, I think, 52 in some frequency bands. So anything above 40, we're really kind of at the noise limit of the directivity. So yeah, I mean we're there.
So now the input power at that point is 0 dB.
Is exactly 0 dB. So if you downloaded the power meter software that comes with this USB, it's free, and you put that in there, you would see
how we can do that. So
if you type in the U8485 on the Keysight website, there's a free power meter software. So you can plug this into your your PC and just use it as a power meter anywhere, right? So you could use it to calibrate this signal generator, because who knows how accurate these guys' measurements are. But you can do whatever you want with that, and it gives you a lot of flexibility.
So the USB can work as a power meter.
But yeah, this is effectively a power meter on any platform, as long as it has USB power. So this tells us that from minus 20 to 0, we're not seeing any response. This is the input match. And then if I go and say, okay, well, it's great, and I should see almost 0 dB return loss in all cases. So let me add some new traces.
but you were showing S11.
I was showing S11, but let's take a look at the
Insertion.
the insertion loss, correct. And it's a reciprocal device, so it doesn't really matter whether it's S12 or S21. But it's right around 0, and it's flat with power, right? Which it's a bullet. That's what we expect. Where are your preamps? Do you have them? Do you mind if I take a look? Maybe I can figure out.
To take the data, it's better to put it on Excel or just
I'll talk about that when your colleague gets back, so he doesn't miss it. But yes, you can talk about it. Let me just go take a look at what you guys have. Oh, that's a big frame.
Yeah.
Let's see. It's all BNC.
Yeah.
So it looks like it's channel. Oh, so the gain is maybe adjustable.
Yeah, we can adjust from this game.
Okay, so let's plug it in. I mean, we can take a look and see if we can maybe do something where we can set the gain to maybe 10. Yeah, that's fine there. What we'll probably do is I'll move this and put it on top of there.
If you don't need to.
No, I definitely don't need that. Okay, can we... Oh, so this is a differential input as well, right?
Yeah, it is differential.
Okay.
Differential channel.
Differential to single-ended output. You know what? I'll bring an amplifier next time. I'm not going to take a gamble with this thing, because if it's differential gain, I don't want to mess around with it too much. But we can do the gain compression, and you have access to all of that. The other thing that you have access to on this is part of the software upgrades that you can get down the line is a full spectrum analyzer. So you can actually look at not only the main tone, but you can look at the harmonics that are generated by your amplifier. So you could do what's the at single input, what's the harmonics, and then if you connected, this is a vector signal generator, yeah. You could use this as even an analog. You put it in here and use an external combiner, and you could do a there's an intermodulation app, so you could do swept IMD, and it would control that signal generator as if it were part of this instrument, and it would say, okay, we're going to sweep either the tone power or the tone spacing or the tone center frequency and keep the tone spacing and tone power the same. And it would do all of that for you for amplifier characterization. So how often are you doing amplifier tests then? Not very often? Okay.
So for the antenna, just we make the S11
That's it.
measurement. That's
pretty much it. It's really, antenna measurements are usually pretty simple. The only time that you have to worry about it gets a little bit complicated is when you're doing a radiated pattern test, right? So do you guys have a positioner and an antenna chamber? No? Then all you're going to be doing is maybe putting some shielding around your antenna.
Yeah, we have a microwave shielding box actually.
So you have a shielding box, so put your antenna in, we'll do an S11 measurement. That's about it. Antennas are really easy to measure. Like I said, the only time it gets difficult is when you're trying to do quasi-optic experiments or like far field measurements, and you have to do kind of calibration. Sorry?
Radiation pattern.
Radiation pattern testing. That's where it gets much more complicated in terms of the calibration and making sure that you're really doing, you have to have a standard gain to make sure that you know what the gain of the antenna is so that you can get the EIRP and the total gain of the antenna.
So in terms of impedance,
Yes.
so this is 50 ohms, right?
Correct. So
if we have other measurements like
So-
75 or something, can we do it?
So you can. What I would recommend that you do there is that there is a 50 to 75 ohm balun that you can buy from Keysight, or you can get it from somebody else. You can put it on here, and then you can change your system impedance here. So under system, take a look again. Where is it? Alright, this is the perfect use to use the help function. So let's go here, and then our keyboard is over here. Hopefully I'm typing in the right place. Okay. So, port Z conversion, this is what you want to use. So this looks like it's probably under Cal. Let me close this. Under the Cal fixtures. Oh, okay, let's go back to the help file. Yeah, so you put different matching networks there to simulate those. You So this is under, looks like just under the fixture, so it should be there. Let's go minimize this again. Oh, there it is, okay. So under port Z, you can say what it is. So you can actually,
So it was in Cal?
Cal fixtures and port G.
okay, so under, so what you want to do is under Cal, under fixtures, under fixture setup,
Port Z.
port Z. And so if you have 75 ohm, might be the most common if you're doing some kind of cable TV type of application. If you're doing, if you know you're using the balanced mode, so for example, if the differential impedance might be 100 ohms, but effectively the port impedance is still 50, so it doesn't matter for that application. But if you're applying, if you have a balun or some other kind of impedance matching network, you can say, well, actually, based on this balun that's 50 ohms to whatever the system impedance is, you can use port Z and actually put a full complex impedance in there if you know exactly what you're going to be measuring.
So arbitrary impedance we can.
Yeah, so you can see under port Z, it tells you, R plus JX. So it uses that format. And it can be applied different, you just have to click enable. But there, you can have port 1 be one impedance and port 2 be a completely different impedance. There's no, tie where they both have to be the same. It's completely independent. And then if you're going to do matching, like the other thing again, so exactly. So under format, you can access the Smith chart. And again, if I really want to, I can just say, where is the Smith chart point for this? And so if I put a marker on there because, it's really small. But I can see here it's 47.38, 1.62, and that's the effective capacitance at that frequency. So this is a power sweep, that's why you're not really seeing it change, right? So at one frequency, you're going to get a fixed return loss of this piece. Do you guys have any antennas or anything that you're wanting to measure?
We have EECS.
BNC antenna? Sure, that's
Okay.
fine. Yeah. Okay, so you got some of these ones here.
This is the small free box.
You have a field fox?
Yeah.
You guys got some field foxes here for your labs? For
Yeah,
teaching?
for-
Yes.
Let's end the BNC. Now we just need end the SMA and maybe. So if you do this on the field fox, do you have the field fox here?
Yeah.
Do you want to pull that out? Because
Yeah.
I mean we can, I can show you kind of what that looks like on the field fox. Okay, you had a question about saving data, so when he comes back, I'm gonna make sure that I get your question answered. Looks like you have a like a fiber optic setup over here, maybe for doing beam alignments.
Yeah. Lenses.
How are we doing on time? Just give me a time check here.
3:35.
Just want to make sure that
How?
I was gonna stay till 4:30. If you guys say, hey, we're done with questions, like I'm gonna come back, right? This is not a one time. I'm here and then see you guys later in 6 months. We'll schedule this again, but the thought was to just get you guys going on this. Let's make sure that we're here, and then we'll do another follow-up session that's with devices if you guys have some, or I can bring my own, and then we can do some typical measurements that you guys may want to make. Okay. So let's take a look at your field fox. Is it type N or is it also okay?
Yeah.
So it is N. Okay, yeah, perfect, thank you. This is a 4 gig field fox. And what I'm going to do is, rather than do multiple adapters, I'm just going to connect directly to the field fox. So you had a question about Mansoor, right?
Yes.
Yeah, Mansoor had a question about saving data. Okay. So what are the file formats we have? So if I go to System, I can just take a
Save recall.
yeah. Well, I can just take a screen image, right? So that's the most basic thing that you want to do is just basically say, okay, I just want to print. Print a file. Done. That's my screenshot, right? And it'll take whatever's active here. You also have under the save recall, like you said. So you want to save, and you can see it says save state, but then you can do
Say type, maybe? Or?
save other.
Uh-huh.
And you can see save data is what you want to do, or you
Oh,
can
yeah,
save the
nice.
screen, right? So one of the two.
Formats, different
So the
formats.
formats
right?
there, so you can see if I'm just trying to save the screen, right? And I thought I clicked on save data, but yeah, so you can see it has CSV files.
Mhm.
And it has S2P files or S1P files, depending. If you're doing an antenna, it's going to be an S1P because it's only one S parameter. If you're doing a full like amplifier or LNA or mixer, you're going to get an S2P file.
Just, I have a question regarding the S2P file.
Yeah.
Previously, I did it. Then while I was importing in ADS, I was not showing. It was not showing what I was seeing here.
Okay.
So is there like a reference thing that we have to take care of, or?
No, it should be the same. So, I mean, I'm not the ADS expert, but I can definitely.
Because the ADS has the option to import the
Correct.
S2P.
Yeah, no, and it should be plug and play because S2P is a worldwide standard. That's right.
The battery is low.
Yeah, it's not even powering up.
There's the charger.
Here or
Yeah. Oh, yes.
So,
If you need help with ADS, I can put you in touch with our ADS application engineer. His name is Boris. He works at Harmonic.
yeah, I mean, it's should be pretty plug and play. I mean, something like figuring out how to import an S2P file, I should be able to figure out myself. But if you need something fairly detailed, Boris is the right guy.
Even for momentum. Because
Yes.
I have a lot of momentum.
Yeah,
Sure, yeah.
so Boris is the right guy to cover all of our ESOP applications.
If I can get your email.
Yes.
Yeah.
Right, so we wanted to take a look at the S parameters of the antenna, right? That was what we were doing, I think, with this. Like, why do I have a field box all of a sudden?
Should I sample
You want to connect the antennas to the PNA?
That's fine, we can look at it here.
No, just the momentum. It's not a specific momentum.
Same.
So this is loading. So this one, I think it completely died, so it's going to take a little while. The other thing that you can do, so are you managing the lab?
Yeah.
Sorry, I forgot your name.
Amin.
Amin?
Yeah.
So Amin, what you can do is you can sign up on our website,
Mhm.
and if you say I have a field fox, I have a PNA, I have a 9000 series scope, anytime there's a new update for the firmware, it'll actually send you an email saying, by the way, and it can do this on a monthly basis, or you can say every 2 weeks, or however often you want. It'll say you have a new option available to you. So
Okay.
So a network analyzer mode, right? So this is the, from start to finish. If I go to format here, it's a little bit different on the Firefox. But I can go to format, and instead of log mag, I'm going to go to Smith chart. So it's the same thing, right? Except it's just handheld. Now, obviously, if you do this, you're seeing your Smith chart, right? And so seeing it varying versus frequency. So the thought though is if I do this versus and I actually do this and you can do you have a BNC cable? This is a really good demo for us to take a look at.
Yeah, we can.
Yeah.
Just to be on
BNC,
BNC,
right?
right? If you open that up for me. This is going to give you that, you know when I said like you can't really rely on BNC cables? This is a live demonstration of why you shouldn't rely on those BNC cables. Right? So obviously this is, do you have a BNC female to female connection? Those are mostly.
I think we might have some of the last two ones.
You have something left? Yeah. You can check. And also check mine.
Is this just a mount for little components? Is this what this is?
A resistor and yeah, some. Maybe it's just two, I think. Just
Do you wanna?
just done.
We can.
Yeah. It's to put some capacitors, I think,
Oh, yeah,
or some
capacitors,
devices over there. I think we have, but we left. I mean,
So you guys make these yourselves, or were they?
yeah, I think so. Just about the other technologies, I already done.
Okay.
The other books?
No, all remain to my materials.
Okay, good.
Perfect.
This work?
Yeah, absolutely. So let's do line mount here. So, you know, if I take a look at this, and maybe actually you want to hold this, you know, as I bend this cable, I'm seeing a little bit of response difference, and that's in magnitude format. But let me go back to now to the full Smith chart, and based on what I do here, you can really see, you know, even just moving the Smith this thing, I'm getting a lot of difference on that Smith chart, right? So if I'm trying to do an impedance match and I'm using a BNC cable, you know, again, like maybe I can get away because like right now I'm doing that full sweep from you know
Megahertz.
to 4 gigs. But this is not even the 13.5 that we were looking here. So that's why if you're trying to do this with BNC, you can really forget about it because depending on how you position this, and obviously, you know, with an antenna, depending on what's close to it, it's going to be entirely different. So this is why you guys really want to make sure you get good VNA cables for the measurement.
So can you suggest maybe like for this, because it's the range of 13.5 gigahertz, and what types of cables?
I will absolutely suggest some good
Yeah.
cables for you guys.
List of cables.
So that's kind of a quick idea of why not to do that. So
Can it give us the reflection coefficients, the VNA?
the VNA, yeah, absolutely. That's what S11 is, right? So that's what you were measuring here, right? You were doing it versus power as a power sweep, right? But if I went to frequency, I mean, I'd have to, every time I change it, I have to do a count, right? Because here I did it for 3 points, but if what I was showing before was a sweep versus frequency.
And we can change it to Z parameters, right?
Yeah, so under format here, we can go to that, but then there's also some other formats. So you can actually look at, you know, you can look at that. You can also look at temperature. Let's see what else we really want to do here. So if you want to do, actually, you had a very good question. So you said, how do I do Z parameters? So I have the S11 here, and I want to do format and I want to take a look at the linear magnitude. And then what I can do under the math, under analysis here, under conversions, I can go and say, oh, I would like to see the Z reflect. And if I go to I mean, obviously this is 50 ohms, so I'm going to see roughly 50 ohms, right? But this gives me the magnitude of the Z reflection. And that's why it says 47.34 units, because it's magnitude only, right?
But we can change it to R plus JX.
You can, but you're not going to, okay, so the issue is how do you plot R plus JX? The easiest way is just to do it on a Smith chart, right? So if you turn your format and go back to, sorry, if you're going to turn off your math, let's turn off the conversions off. We go to format and go to Smith chart. This is R plus JX, right? So this is R and JX is.
Or it will give S parameters in it.
So it depends on what format you are, right? So the S parameter is.
Because this will give us the S real and imaginary, I think.
Yes. But depending on what format you're plotting it in, right? So if you wanted to do it, you could plot it in polar, and that could give you S in real and imaginary, right? Or you could look at it on the Smith chart.
I mean directly converting S to Z.
Yes. So on when you do Smith, that's what it does. With the S11, it takes it and plots it on the Smith chart, which is effectively R plus JX, right? So let me just save something really quick here. Let me just save this thing, just in case I need it. Okay, so that's the power stage state. If I preset, this is an uncalibrated measurement because I'm just going to go back to here. But if I go to format and I go to Smith chart, I have my R plus JX. The issue is, okay, well, how do I get this into an R plus JX plot? Is that, excuse me, like, do you understand what I'm saying? Because R is one thing, JX is another thing. So how do you do that? You can do one of two things. You can just use the equation editor and get R plus JX based on, the S11 and doing the math to get to impedance, and you can plot that in the equation editor. Or you can do this and then say, I want it at 5 or 10 different frequency points, and then I can say, I'll just use the marker, and every marker that I put in, right, I can change the frequency and say, I would like to know at 5 gigahertz, I'd like to know at 5 gigahertz, I'd like to know at 1 gigahertz, 1 gigahertz, right? And now I have R plus JX at all those different points. So it depends on what exactly you want to do. If you just want to see a plot of R
Versus frequency.
and then a plot of JX versus frequency, you can do that. You just use the equation editor, use S11.
There is no built-in function. I think there is a built-in.
There's a built-in function to
But
get.
it converts the S parameter to Z directly.
Yeah, so I think that's what I showed you. That gives you magnitude of R plus JX. And there may be a way to get R and JX, but again, because they're two separate things, like it's kind of hard to plot that versus frequency on a linear graph, right? You kind of understand because it's effectively it's two plots. So I think there's something in the equation editor that might be built-in equations already. And I think there's an example for that, but I don't know if it exists. But I can take that down as a question, and when I come back, I'll say this is exactly how you do that.
Yeah, we can see that in the field fox.
Yeah, in the
Real
field fox. So-
real and imaginary.
But in the Smith chart format, or it
Like
gives
real frequency and imaginary power frequency versus
Yep.
frequency.
so you can do some things like that. So if you go to format here, so you can go linmag, we can do the math there, and we can do analysis, conversions, Z reflect, and this is the linear magnitude, right? So if we go to, that's the 47. Let me see if I just here, let's go to trace, inside another trace. Let's go to we're measuring S11, we'll go to format, we'll go to, instead of linear magnitude, let's go to imaginary. Does that sound about right? Yeah, that looks
that's-
reasonable.
yeah.
Yeah, this is exactly, I think, how you would do it. Yeah, so I think you would actually probably, in what you
Then
probably,
you convert now to Z.
it's already done in the conversion. But what I'm curious to see is if instead of doing format like mag, let's see what happens if I do real. Yeah, so that's how you do it. You do real and imaginary, and then you would do it, and you do the conversion into Z reflect because you're measuring an S11, and you would get it that way. And then you can, and under the math functionality, you know, there's the Z reflect, but there's also Y reflect, Y transmit, a number of other things there.
It's math analysis and conversion.
Conversions, yeah. So we covered that. I think I wanted to talk a little bit more about noise figure and why you have the other ecal, right?
Yes.
So I think it might be somewhere here. Yep, there we go. So one of the things that you can do you see this is a kind of weird looking thing over here, is you can actually use this particular ecal as an impedance tuner before, you know, still using this as the test port. And what this will do is, remember how I said there's a number of different impedances inside this device? There's about 7. And so what it'll do is it will set itself to different impedances and sweep around the Smith chart so that when you do your noise figure measurement, you can get true 50 ohm noise figure, right? So if you have a device where you know it's not exactly 50 ohm, but it's around 50 ohm, maybe it's 48, and you really want to know what's the exact noise figure if this device were 50 ohm, you would use this as part of that. So let's go into the measurement, and I'll just kind of talk about this pretty quick because I don't want to spend too much time on it today. When I bring in an actual LNA, let's go and do the measurement, and then I can show you guys how to do that. So under noise figure cold source, I'm just going to hit OK. And because if I didn't click a new channel, it gives me the option of overwriting this. That's what I'm just going to do for now. So again, I have the option of doing a linear frequency sweep, a CW frequency sweep, or a segmented sweep. I can do power. Power is only going to apply for the S parameter portion. And what this does is it uses a cold source noise figure measurement technique. So if you're familiar with noise figure measurement, usually it uses something called the Y factor. So the way that you do this is that you usually use a noise source. You guys may or may not be familiar with that. Have you guys done any noise figure measurements before? So what you do is the noise source has an avalanche diode inside it, and either the diode is not biased at all, so it's off, and then you're getting the ambient temperature. So, you know, on a hot day like today, it might be 300 degrees Kelvin, 301, and then on a and then when the diode is biased in such a way that it's having avalanche breakdown, it just generates broadband noise. And what we do is we characterize the excess noise ratio of the noise source. So that means how much higher is the noise power that's being generated when it's in breakdown mode, right? And so typically with a spectrum analyzer, what you would do is you do a calibration by looking at the difference in noise powers relative to the the noise figure of the receiver itself, and then you would put in your DUT, and what you do is you do a measurement with the noise source off and noise source on, and based on those two power measurements, because you're looking at the output noise power generate at the output of your DUT, you're able to characterize the gain of your device because you have 2 points on a curve, so therefore the slope is going to give you the gain. And you're also able to go back and figure out what the y-intercept is, which is what happens when you put in no noise power, right, theoretically, and what's being generated by the device as its just inherent noise. Now, with the PNA, we have access to a number of things that we don't have access to on a spectrum analyzer. On a spectrum analyzer, there's no way to do any kind of correction, right? You might be able to put in a fixed value offset for a cable or an attenuator you have, but you can't do mismatch corrections, right? And typically with those avalanche diode sources, when they're off versus when they're biased on, the impedance of that noise source is going to change, right? So the mismatch between the device and the noise diode is going to change, so the amount of reflected energy is going to change, and therefore the whole system is not well characterized in terms of the mismatch error that's there. And typically when you're looking at an active device, the amount of noise it generates, and this is just called its noise parameters, is dependent on the source impedance. So remember that source impedance is changing because of this avalanche diode, and I'm hoping to get an idea of what the actual noise figure is of this device. So with the PNA, we do something different, and that's that cold source technique. So what we do is we first do a gain measurement, and this is a S-parameter measurement device, so it's the best thing for measuring gain. And then what we do is we turn off the sources inside the network analyzer and just use the noise figure receiver, which is a dedicated receiver with an LNA and some bandpass filters. It's all built in line with some switches inside the network analyzer. We switch over to that, and we just measure how much noise is coming out of your device, and we know what the ambient temperature of the network analyzer is. So the gain gives us the slope of the curve. The noise power at ambient gives us a point on that curve, and now based on the slope plus that 1 point, we can now figure out what the y-intercept is, which is what we're trying to find, which is the noise figure. So it's a more accurate way because when you measure gain with this, you correct for all the mismatch effects, right? So sure, Jill will send you the link for the webcast that I did called Mastering Noise Figure Measurements. I spent a full hour going over that, and I strongly recommend you go through it before we come back and do the measurement the next time. That'll give you a really good idea of all the fundamentals of noise figure, plus there's some other application notes that I reference in there. If you want to spend more time learning about noise figure, it's a very good resource. So after all that, you get your noise figure, you've got your gain, and you're able to do this without changing the device. So for example, when you're measuring an LNA, you can do gain compression, you can do noise figure, you can do IMD, if you have the internal combiner, all with one setup, right? There's no connections, reconnections, disconnections to the device under test. So this is why it's super convenient to use this device. But and the last thing is the noise figure, right? So the part of the noise figure setup is you can see, so under impedance states, you see how it says noise tuner? There's none selected here because it only has this ecal connected. So let me close this and let me connect the other ecal, and we'll talk a little bit about what happens there. So the reason that we got you this ecal is so you could use this one as a noise tuner and also use this one for calibration. Now this is a little bit different. This is something I would recommend that you use. If you have educational labs, this is the one I would recommend that you use. And I'll talk a little bit about why that is. So the memory structure on this is a little bit newer. You'll notice it uses a micro USB port instead of the standard USB A to B. But what's really kind of cool about this is you see right away that green light went on. So it does not have an oven. So it means that the loads inside here, there are a number of loads, but they're not as well characterized, so you don't get the same level of uncertainty in your measurements with this as you do with this, right? This is a good economy calibration. This is a metrology grade calibration, right? So this is basically calibrated using standards that we get from NIST, right? If you guys know a little bit about, do you know what NIST is? Have you heard of that? It's the National Institutes for Science and Technology in the States in Boulder, Colorado. They're the ones that say this is how much exactly 1 kilogram is. This is what 50 ohms is. They do all of that. So we get standards, and this is about the second best thing from the standards that we get from NIST, right? So you can, if you go to one of those labs, you'll get the best calibration. This is what I'd say is a close second. This is designed in a way that it's for educational use, for manufacturing use. It's good, but it's not as good as this, right? And it's about a third or a quarter of the price of this. So that's why there's a difference here. So it's still, like I said, good. You're still going to be able to get accurate S-parameter measurements. It's just, for example, remember when I said you could get about 42, 47 dB of corrected values with this? With this, you're looking closer to 37, 39 of S11, directivity corrections, right? Still, that's still a pretty good measurement in terms of the uncertainty. It's just not as good as what you're able to get with this. So what you do with that now is now you can do, if we go back and go to under this and go to noise figure setup and go to noise figure now. We should have access to the tuner. Maybe it just takes a little while to correct it. And I need to connect this in series. So there's a setup diagram on how to connect this with this. It actually tells you as well. So it says here's where you would connect the noise source. And this kind of goes into here. And then this would plug into there to be able to go in as the noise source. And now you have the tuner accessible. Okay. So we'll do that measurement when I come back with a real device, because I could set it up now, but doing the noise figure of a through is kind of meaningless, so it doesn't really make a difference there. And I would update that firmware before I come back. Can you guys do that for me?
Yes, of course.
Okay.
The latest is 13.25.
13.25.
Yeah.
It should be on that na.support.keysight.com.
Yeah, so I'll download and just install.
Yeah, just install it there. Make sure that it's not a day it's like a nice day like now where it's not thunderstorming like last night where you might have some power outages in the middle of your update.
It was raining all throughout your demo, by the way.
It's beautiful now. So
And I do not need to remove the existing version, right? Just
it'll overwrite it. So that's
overwrite, okay.
It'll delete the existing version and install the other one. So. Okay. Do you guys have some resistors and capacitors you want to try to do a quick measurement on here? Because obviously looking at the through is interesting, but maybe you have some RCs that you want to take a look at.
Can I measure I don't know, we have some carbon fibers for measuring capacitance and impedances.
Some what?
For carbon fibers.
Some carbon fibers you plug into here. Is that what these are for?
No, it will not be that much easy. So, but we can bring some sample.
I think what the students were doing is doing small coils with wires and trying to measure.
Yeah, we can do something like that if you want.
But he has also capacitor or something. Oh, this
So regarding that, you will send me an email.
Yeah, I actually tried to send it through my phone, but it didn't go through, so I have it in the chat. I'll send it to you. If you want, I can write down my email address.
Yeah, that would be good.
Yeah, I'll write it down because my name is special. SHIR.
So I mean, like this can be an interesting device. Maybe this is going to give us a good RC.
Kind of figure use of
It should be a filter, right? This is what we'd expect. So let's see if
Yeah, that's right. Sure, Joe.
we have everything already, right?
Yeah, I think you were on the.
I mean, and it's
Same.
yeah. We have everything there.
Yeah, if you have any questions, please feel free to give me.
Yeah, I mean, we're expecting the links for the YouTube videos, and
Yeah.
in case you have the full PDF of the help files, and if it's possible, the hard copy we recommend, like it would be great for us.
PDF of the file for the help file.
Yeah,
So
like, whatever.
it's not a PDF. It's a browsable
HTML.
web help. Yes, it's
HTML or CHM. No?
CHM. I think that's what it's called. I don't
Okay,
know.
that I think you can find on NA.
It's on the NA support website as well.
Hard copy, as you said, we don't make.
We don't have them, okay.
We like to save trees, I guess.
I mean, all the equipments we are getting like one copy of our two so that we can keep with them, and student can sometimes easily find
Yeah.
instead of searching.
Yeah, we find, and I'll give you guys actually another cool thing that you can do with our equipment. And this is why we're Keysight's best. It looks like I have some
Something fell. So
it's a resistor, so that's why I was like, oh, why is this? Thought I had some good resonance going on there, but
I can bring some. It's fitted.
right. So depending on a good day, I might have something there. So let's put a marker here. Let's go to around 1 gigahertz probably. It's not as dramatic as I hoped it would be. We can kind of see that there's something here. So let's go to that. So depending
Just
on
range maybe of frequencies.
this is looking at start. So if you look at the frequencies here, starting at 755, going to 2.755. So depending on where you're going to be, you're going to have different things. So you have a reasonably good match at some frequencies, and then others are not so good. So do you know what the capacitor is?
No, I don't.
The thing is, it's not
Think
just the capacitor.
nanofarads most probably.
Right? It also depends on frequency, right? The
Mhm.
capacitance.
Yeah.
But
Yes,
the issue with these kinds of mounts is that at high frequency they're not very good. So you might be
Yes,
able to
of
do it
course.
at like a couple hundred megs, but
Mhm.
surface mount is the best way to go. Do you guys have PCB circuits or anything like that? So what do you guys do for your labs now for the students? What do you get them to measure?
Oh, well, I'm developing a wireless EEG. So we ordered the
What is
PCB.
the energy transfer? Or
No, it's electronics.
oh, okay, so
It's how his
Oh, okay.
area.
So for one of the things that you can do, right, is if you have one of the super easy labs to do is just basically if you have a 50 ohm strip line And what you can do is you can just put some surface mount loads, right? So some resistor, some capacitor. You have the feed line there, so you can say, you know, hey, measure what the impedance of this is. And you can do that even on the field flux, right? So you can set that up, do the measurement at 3 gigahertz, for example. And by the way, this ecal is also compatible with the field flux. So both of them are, so you can do the cal there. And then what you can do is, okay, so now you know what the impedance is. You give them copper tape that's cut to the right 50 ohm width, and just say, okay, design your single stub matching network, right? So they would say, okay, what's the distance I have to be from the load? They would put the copper tape down. They could do some quick soldering there, and then they would be able to trim the copper feed line for the length of the stub till they get the right match. So that's a super easy lab to do single stub impedance matching.
I got it half the way. You said we put the feed line, 50 ohms, and then some sort of load?
Yes, you give them a PCB, right? So,
Yes.
so the idea would be you just do, so this is the, you could do an RL or an RC depending on what it is, right? In series or in parallel. So let's say this, and maybe you have a nice via pad over here. And you have this kind of sort of network, right? And this is an SMA. SMA are usually is nice because it's small contact. It's not going to snap off the PCB board. But this is 50 ohm, and this is like a copper trace, right? And as long as it's not coated in an isolating material, you give them the right amount of feed line, and then what you say is, okay, they measure this impedance. If they know what the length of this is, right, they can also know how far it's been moved on the Smith chart, so they can extract what the impedance is over there. So and they can physically measure that. That's not a big deal. But then what you can say is, okay, based on this, create a single stub matching network to do this. So then what they have to do is say, okay, based on what the impedance is here, I know what the impedance is here. I want to be able to create. I can place the single stub based on the D here that I need to know, and then the L. And then if because of non-idealities, it's not going to be perfect. They can solder this down to make sure that you get a good electrical connection, and then they can start trimming with the X-Acto knife to make sure that this ends up being the right length, and then they can say, oh yeah, we calculated 3.2 centimeters. We found out it was 3.05. That's the right length. And that's the right matching number. So that can be an interesting experiment. It's very. I think I've seen this as part of the MIT's educational kit a couple of times. So.
Yeah, I mean, students are actually using these types of coils to check with the field foxes. So they're
see these resonance, yeah.
These attenuators.
Okay, so these are some attenuators and stuff like that. And this is a couple. This is a full couple.
Couplers.
Yeah, so this is exactly it. So you can look at the so if you have 50 ohm loads, you can do like, okay, what's the coupler from to the, this is coupled to the out port. So if I put a signal into the in, I should see it here, but I should not see it here because this is leakage, right? This is undesirable effects. So you can actually characterize the coupler and give them the full S parameters in terms of the isolation, directivity, loss. And you can say, you know what, one of these is inside, well, you've got actually two of these inside the field flux, right? Because you've got one on the forward side and one on the reverse side, right? And so, same thing with this network analyzer over here. And so this can be a good way to say, this is why you can't measure. Remember when I said the limitation's really like that -40, you can't get any better? It's because if you take a look at the, the coupled sort of to the import, right? So for example, if I send a signal here, this is the load that I'm measuring right on the out. I'm gonna have some leakage on the out, even though this is gonna be my reference signal that I want in the import here, but I'm gonna get some undesired leakage. And the ratio of that leakage versus the loss in the coupled arm, the coupling factor here, is what's gonna give me the limitation as to how small of a signal I can measure.
Sorry, I gotta get going. Very nice meeting
Yeah.
you. I'll get back to you about
Yeah, sure.
Yeah, what time is it?
It's 4:15.
Okay.
Very cool. It was nice to meet you too.
Yeah.
Take care.
So, does that kind of give you guys a starting point for all this stuff? Is that pretty good? Do you have any specific questions before we wrap up for today?
Thank you.
No? I mean, again, I'm going to come back. We'll spend another half day at the very least, because this was let's call it 2.5 hours. Technically, you guys have 7 hours, so we can do this another 2 times, and that's fine. Or we can come back and spend 5 hours at a time, whatever you prefer. So one of the things I've done is I actually kind of used to do what you guys did, which is run the RF and microwave lab at University of Waterloo. So I've done that before. If you need help designing experiments, you can give me a shout. I can be part of the training next time. You can say, hey, how would we do this? We're thinking about doing this experiment. Can you help us refine this? So we can do something a little bit more detailed next time.
Yeah, sounds good.
Okay?
Yep.
Awesome. Well, it's a pleasure meeting you. Pleasure
Yes,
meeting
thank
you.
you.
Thank you.
Pleasure meeting you. Same here.